Okay, so let's do chapter 9, SP5. You'll find this kind of a problem is talked about in section 4 of chapter 9. Question is found on page 191. So we have a pipe with a circular cross section, has a diameter of 8 centimeters. It narrows at one point to a diameter of 5 centimeters. The pipe is carrying a steady stream of water that completely fills the pipe and is moving with a speed of 1.5 meters per second in the wider portion. So this problem, the sketch for this problem is really on page 188 in section 4. Anyhow, so we're going to wind up drawing this. A pipe with a circular cross section. Circular cross, so it's a pipe. A standard pipe. Think of a really big straw. A diameter of 8 centimeters. So 8 centimeters. It narrows at one point, so it goes on straight, and then it narrows to a diameter of 5 centimeters. So it looks like this may not be too much to scale, but hopefully you'll be forgiving. And then it continues on. The pipe is carrying a steady stream of water that completely fills the pipe and is moving with a speed of 1.5 meters per second. So the speed here, we'll call this section 1, we'll call this section 2, is 1.5 meters per second. So this water is coming in, and then the pipe narrows. What do you think is going to happen to the speed of the water in this section, in this smallest section? Well, perhaps you have played with a water hose where the water is coming out of the hose, and then you put your finger over part of the hole where the water comes out, and what happens? The spray comes out faster. And that's because water is essentially an incompressible fluid. You need a lot of force to compress water. In any event, we're going to make water our incompressible fluid. So since water's coming in at a steady stream, it must go out at a steady stream. If it doesn't, then we're going to have a buildup. The density is going to get greater, or the speed must decrease. In our problem, the speed's going to stay steady here. So in order for the same volume of water that's going through this section to go through this section, the speed must increase. And you may remember the formula for that. That's V1 A1 equals V2 A2. So this is the speed in this section. We call it V1. We'll call this section 2. So that's V2. We don't know what it is, but our answer should be that the speed here is greater. This is supposed to be a question mark. Is greater than the speed there because the area is smaller. Remember, we're not given the area. We're given the cross-section diameter. We're given the cross-section diameter. So we're probably going to have to calculate what the areas are, the area here and the area here, and then finally what the speed is. That's my guess. Let's see the problem. So A, what are the cross-sectional areas of the wide and narrow portions of the pipe? Exactly as I said. So we're going to count this as area 1 is equal to pi r1 squared. It's circular, so we know we have a circle. So this is going to be the area of a circle. So that's equal to pi times r1 squared. Well, if the diameter is 8 centimeters, then the radius is 4 centimeters. Let's put the centimeters in, and we got to square it, right? R squared. So that's equal to 16 pi centimeters squared. Yes, it's okay to leave it like that, or if you want, you can multiply it by 3.14. I'm going to leave it like this because I'm going to bet there's going to be some cancellations going on. So what about area 2? Well, that's equal to pi times r2 squared. So that's equal to pi r2. Well, that's 5 centimeters. is the diameter. So the radius is then 2.5 squared. So our answer is, I'm going to say 6.25 pi. Again, centimeters in here, right? So 2.5 squared. Yeah, I'm right. 6.25. 6.25 pi centimeters squared. And just notice that if we did divide these, the pi's would go out, the centimeter squared would go out. That's why I'm leaving it. I'm betting we're going to have some cancellations going out. So that's the answer to A. Now B. B says, what is the speed of the water in the narrow portion of the pipe? Well, that's just a plug-in. Here's our formula. So we get V1, A1 is equal to V2, A2 plug-in. V1 is given as 1.5 meters per second multiplied by A1. A1 we have 16 pi centimeters squared. Notice I have meters and centimeters squared. That's normally a no-no, but like I said, I think we're going to get some things to cancel out. You can change it to meters here if you're more comfortable with that. That's fine. I'm not, because I really think things are going to cancel out. V2 is our unknown, but we do have A2, 6.25 pi centimeters squared. Okay, let's see what we can cancel out. We can cancel out the pi's. Cancel out the centimeter squared. I knew it, didn't I tell you? So what do we got left? We have 1.5 meters per second times 16, right? 16 was from here. That's going to equal this side. Okay, so we have 6.25. The units canceled, and we have V2. So let's multiply this together. We get 1.516, so that looks like it's 24 meters per second is equal to 6.25 V2. Remember, V here is velocity. It's not volume. So V2, the speed in the smallest section, is equal to, divide both sides by 6.25. And I get 3.84 meters per second. When we started, we said that here's the speed, that the speed of the water would have to increase because it's going from a large volume, large cross-sectional area to a small cross-sectional area. So in order to keep the speed of the water, the volume of the water constant, the speed of the water here would have to be greater, and that's what we got. The speed here in the largest section was 1.5. The speed in the smallest section is 3.84 meters per second. So that brings us to C. Running out of room, so hopefully it's not too bad. Is the pressure in the narrow portion of the pipe greater than, less than, or equal to the pressure in the wide portion? Okay, so it turns out the logic we're going to use comes from Bernoulli's principle. And the logic we're going to use is the greater the speed, the larger the pressure.